Hi there, my name is Dr. Dorothy Buckley, and it is my pleasure to welcome you to this video where we will discuss episodic memory. So what is episodic memory? Episodic memory is essentially a subsystem of memory responsible for the retrieval of personally experienced events that's often accompanied by the feeling of remembering. So, just to reiterate Tulving's distinction between episodic and semantic memory, we'll start with episodic memory. Episodic memory allows you to access a specific event located in a particular point in time, right? So, essentially, you engage in what's called mental time travel, either going backward to relive earlier episodes or sometimes into the future if you want to anticipate and plan for events that haven't occurred yet. Uh, Semantic knowledge or semantic memory, in contrast, refers to generalized knowledge about the world that isn't linked to a particular episode or event. So the way that this typically happens is you have many different episodic memories that get consolidated over time, right? So I always give the example of being an elementary school student, okay? So let's say you are 7 years old and you go to school and your teacher, Mrs. Frizzle, is wearing a beautiful dress with maps of the United States on it and holding a globe. And she teaches you a song for how to remember state capitals, and maybe you create a giant map made of sidewalk chalk and memorize all of your state capitals, right? So that's an episodic memory because it is a specific event in your life. But as with the passage of time, right, 10 years later or 20 years later, what you are likely to remember is not your teacher's name and the beautiful dress she was wearing and the sidewalk chalk. Rather, what you're more likely to remember is those state capitals, right? So over time, semantic knowledge is created through thousands and thousands of episodic memories that are stripped of their context or of that particular episode. And what remains instead is the knowledge itself, the knowledge of geography and basic state capitals. So at a short delay, so from the age of 7 to 7.5 or 7 to 8 years old, chances are you're still going to recall the episode, right? You're still going to remember your teacher's name, what she was wearing, the song that you learned, and the sidewalk chalk pictures, right? But at longer delays, the same information will have been integrated into semantic memory in the form of facts about state capitals and world geography. So, when Tolving first proposed the distinction between episodic and semantic memory, it was largely an unsubstantiated hypothesis, and that's why it drew so much criticism. But today, there's actually a wide body of evidence that supports this distinction, some of it coming from cognitive psychology, and much of it coming from neuropsychology and neuroimaging studies. So, one of the most widely used paradigms in cognitive psychology for looking at episodic versus semantic memories is something known as the remember know procedure. So, if you're an experiment and the experimenter is utilizing this procedure, it basically takes place in three phases. So, during the encoding or study phase, participants are presented with a series of items. They might be words or pictures that they have to study, and they are not typically told that they will be tested on those items later. Then, During a retrieval phase, the participants are later shown items, some of which were presented during the encoding phase, and we refer to those items as the targets, and some of which are totally new items that the participant hasn't seen before, and we refer to those as lures. And so basically, in the third phase, the response task, for each item, participants are asked to make either a remember or a know judgment. So for remember judgments, those would require episodic memory. So not only do you recognize the item, but you remember learning that item earlier in the experiment. So you can actually engage in mental time travel from the present response task to the earlier encoding phase where you saw that word, right? So that's episodic memory because you're recalling a particular event that occurred previously when you were exposed to that item. If you were to recognize the item but give a no judgment, you would say that item is familiar to me, but I don't know why. So I don't have an episodic memory of formerly seeing that item, but it is an item that I recognize. And so we would refer to that as a semantic memory, right? So remember, judgments are episodic and no judgments are semantic. So again, with a remember response, the participant recalls the item along with specific details about its occurrence during the encoding phase. So this indicates episodic memory as the participant can recollect the contextual details, the time, the place, the associated thoughts or feelings of encountering that item. In contrast with a no response, the participant recognizes the item as familiar, but cannot retrieve specific details about its occurrence, right? So this indicates semantic memory as the item is known, but the context by which it is known or the original episode or experience is not recallable. So continuing with some of the experimental evidence that seems to support Tulving's distinction between episodic and semantic memory, Henry Molaison, right? The gentleman who had his hippocampus removed to ameliorate his intractable seizures, right? He was left with a inability to form new episodic memories, which is called an anterograde amnesia, but he retained the ability to learn new skills, okay, such as mirror drawing or classically conditioned associations. And he was also able to remember new facts, right, which suggests that his semantic memory was intact, but his episodic memory was not. So in addition to the case of HM or Henry Molaison, there are actually other neuropsychological case studies that support the dissociation between semantic and episodic memory. So for example, if you consider the case of patient KC, KC suffered extensive brain damage following a terrible motorcycle accident. And during testing, Casey could retrieve information from semantic memory to a normal degree. So, for example, he was able to list all of the teams that had won the Stanley Cup in hockey over the previous 10 years. He could also tell you how a car engine worked and how to repair one. However, retrieval from episodic memory was severely impaired. He could not remember any details of his life at all. None of the individual times he had fixed cars, none of his previous motorcycle crashes, or even the details concerning the tragic death of his big brother. Nor could he form new episodic memories. Thus, with KC, we could see both encoding and retrieval from episodic memory can occur without damage to semantic memory. These patients point to an important neurological difference between semantic and episodic memory. In 1997, Varga Kadim and colleagues studied patients who have developmental amnesia. So unlike HM or KC, these patients did not have traumatic brain injuries, at least none their doctors were aware of. Nonetheless, they appeared to be impaired at encoding new episodic events and retrieving events from their lives. Nonetheless, they learned new facts about the world. That is, they learned semantic information normally. Thus, their deficits seem to be solely in the episodic memory system. Therefore, based on patterns of deficits seen in neuropsychological patients, there is a dissociation between episodic and semantic memory consistent with the dissociation theorized by Tolving, right? And dissociation specifically means that brain damage can affect one cognitive system but leave the other intact. So just to reiterate from the previous slide, cases of amnesia often show selective impairments in episodic memory while leaving semantic memory intact. This pattern is seen in various forms of amnesia, including those resulting from traumatic brain injury, stroke, or encephalitis. There's also ample evidence for this dissociation in neuroimaging work. So an interesting follow-up study examined memory for taste. In this study, participants sampled new tastes via sipping on a straw and were scanned as they compared tastes to see which taste matched an earlier one. So this was basically a form of recognition test. And they found that during retrieval, there was greater activity in the right prefrontal lobe than the left prefrontal lobe, supporting the idea that retrieval from episodic memory employs a network that uses the right prefrontal lobe more than the left prefrontal lobe. Other studies of episodic memory show more left hemisphere involvement in many aspects of episodic memory. Nonetheless, researchers continue to find differences between the neural systems underlying episodic and semantic memory. Okay. So, consistent with the view that episodic and semantic memory represent different systems, Prince and colleagues in 2007 found distinct regions of the brain that were active during retrieval from the different systems. So with respect to episodic encoding, Prince and colleagues found that the hippocampus was involved, but a posterior region of the temporal cortex was more associated with semantic retrieval. Moreover, there were differences between episodic encoding and semantic retrieval in the frontal lobe as well. The activity stimulated by semantic retrieval was more in the back or posterior of the left prefrontal lobe, but for episodic encoding, it was more toward the front or interior of the left prefrontal lobe. Thus, this study suggests differences between episodic and semantic memory. So now we're going to continue our discussion by talking about memory processes, particularly encoding, representation, and retrieval. So both episodic and semantic memory can be divided into three important processes that are necessary for any memory system: encoding, representation, and retrieval. Encoding refers to the learning process, that is, how information is initially learned. Representation refers to how we store information when it is not currently in use. And retrieval refers to the process of how we activate information from long-term memory and access it when we need it. There is a strong overlap in how semantic memory and episodic memory accomplish these goals on a cognitive level. So now we will focus on episodic memory, but the process of encoding follows very similar rules in semantic memory. So two University of Toronto memory researchers, Fergus Craik and Robert Lockhart, developed the theory of levels of processing in the early 1970s. Although they originally presented it as a theory that would allow for short-term memory and long-term memory to be considered two different processes of the same system, nowadays levels of processing has a broader application, providing the basis of much of what we know about encoding. Although Craik and Lockhart were interested in levels of processing from a theoretical point of view, the application of the logic of levels of processing can be useful to students wishing to improve their efficiency at learning. Craik and Lockhart were interested in incidental learning more so than intentional learning. Incidental learning occurs when people encode information not by actively trying to remember, but rather as a byproduct of perceiving and understanding the world. In incidental learning, the individual's goal is not to encode information, but to understand and interact with others, find where one needs to go, and so on. So, for example, you don't study the names of people that come to your party, they are your friends. In the course of achieving these goals, one also learns information. So, thus, if asked later who was at your party, you would be able to identify the names of your friends at the party, whereas intentional learning takes place when people actively engage in learning information for a specific purpose because they know that their memories may be tested. In, in intentional learning, we intend to remember something and work hard to do so. Thus, intentional learning maps onto what you typically do in a college class, for example. Your goal is to learn the material specified on the syllabus for an express purpose. Craik and Lockhart considered incidental learning to be an important aspect of cognition. They argued that much of our learning in the real world or in ordinary life is in fact incidental learning. In this view, most of our knowledge and memory is based not on an explicit memorization, but just on processing the events and information we need. For example, we don't normally say to ourselves, I have to remember how to get to Johnny's house, or I have to remember how to chop the onions just right, or even I have to remember the plot of that great movie or TV show I just saw. Yet, in each case, we're able to encode something such as directions, a recipe, or a plot, even though we are not specifically studying this information or trying to learn it, for example, in the same way that you would for a test in college. Another example is when your friends come over for dinner. You try to remember what the person likes to eat and maybe what some of their favorite games are, if they have any allergies. Um, but it's very unlikely that you sat down with like a notebook and a piece of paper and a pencil to explicitly learn that information. You just sort of incidentally, as a result of interacting with them, came to be familiar with this information. Thus, incidental learning is important to our lives. To stimulate such learning in their experiments, Craik and Lockhart decided to use incidental learning. Craik and Lockhart argued that our attentional resources are limited, so we can focus on only some aspects of any particular stimulus. However, people can control what aspects of the stimulus on which they focus. For example, when reading a novel, we can focus on the quality of the writing, the excitement of the plot, and the development of the characters. But it is usually difficult to concentrate on all of these aspects of reading a novel at once. This is where the idea of levels of processing fits in. The manner in which information is first encountered and rehearsed leads to a different depth of processing. Elaborative rehearsal leads to deeper processing, and maintenance rehearsal leads to shallow processing. Thus, when reading a novel, if you only pay attention to the size of the type, whether the book is old or new, or what designs are on the cover, you are engaged in shallow processing. If you are trying to connect the plot to ideas about the world, consider the book's applications to your own life and gauge whether the book is enjoyable or not. This is considered deep processing. If you are listening to someone speak, deep processing means attending to the message of the speaker, whereas shallow processing would include attending to the speaker's accent, his or her raspy voice, or how he or she pronounced the letter R. In real life, we normally are expected to pay attention to meaning, but in rare circumstances, lower level processing may be more important. So we have elaborative rehearsal, processing the meaning of information in working memory, maintenance rehearsal, repeating the information over and over. We have shallow processing, which is processing information by maintenance rehearsal or processing the sensory characteristics. And that produces less remembering than deep processing. And deep processing is processing information by using elaborative rehearsal and engaging in meaningful processing, which results in better memory than shallow processing. Okay? Craik and Lockhart then derived the following hypothesis. When we process more deeply, that is, using elaborative or meaningful processing, we will be more likely to remember the information processed. When we process more shallowly, that is, using maintenance rehearsal or processing for sensory characteristics, we will remember less of the information processed. In retrospect, nearly 50 years later, these ideas appear relatively straightforward, but at the time they offered a new way of looking at memory. They also have clear implications for memory improvement. Process more deeply, and you will remember more of what you are studying. To test this hypothesis, Craik teamed up with Endel Toving to create what is now considered a landmark study. In a series of experiments, Craik and Toving employed a number of new methods, which became standard in much of the research that followed. First, they wanted their participants to encode the information through incidental learning because this better approximates many real-life situations. Therefore, they did not tell participants that their memory would be tested later. Second, they wanted participants to encode some ideas through shallow or sensory level processing and other ideas through deep or meaning-based processing. To accomplish this, To accomplish both of these objectives, Craik and Tolving employed orienting tasks. An orienting task directs the participant's attention to some aspect of the stimuli, either deep or shallow, but does not alert the participant to the potential for a later memory test. Participants were later given a surprise test of recognition or recall for the words. In the orienting task, participants thought that they were being tested on the speed at which they could perform simple tasks involving words, but were not told that their memory for these words would be tested. For example, the participant might see the word beetle and have to decide whether it is written in all capital letters, a sensory or shallow task, or they might be asked something about the meaning. So, for example, is a beetle a living thing? So, if they decide that a beetle is an example of an animal or living thing, that would be a deep processing task as it relates to the meaning of the word. In the experiments, participants were first asked a question, the orienting task, then they were presented visually with the word and asked to answer the question with a yes or no. Some of the questions concerned physical characteristics of the printed word, which would be shallow processing, whereas some of the questions concerned what the word sounded like, so that would also be a shallow question, and some of the other questions were concerned with the meaning of the word, which would be considered deep processing. And the experimental hypothesis was that deeper processing should lead to better retention of the words than shallow processing. In terms of the experiment, this means that the meaningful orienting task would produce better recall or recognition performance than the shallow processing, even though the participants were not trying to remember in any condition. And indeed, this is precisely what Craik and Tolving found in their experiment. When the participants were given a surprise recognition test or a surprise recall test, the items that had been encoded with meaningful or deep processing were remembered better than those items that had been encoded with shallow processing. So again, Craik and Tolving's experimental hypothesis was that deeper processing should lead to better retention of the words than shallow processing. And in terms of the experiment, this means that the meaningful orienting task would produce better recall or recognition than the shallow orienting task, even though the participants were never actually trying to remember any of the words. And indeed, this is precisely what Craik and Tolving observed in their experiment. When the participants were given a surprise recognition test or a surprise recall test, they recalled more of the meaning-based words, or they recalled more of the words that were given a meaningful orienting task than any of the words that were given the auditory shallow processing task or the visual shallow processing task. So thinking about whether a word was an example of a living thing or trying to use the word in a sentence, right? These type of deep processing tasks tapped into the meaning of the word, whereas thinking about whether the word was in lowercase or uppercase, right? That would be a visual, shallow processing task, and thinking about how many syllables the word was or whether it rhymed with a target word was an example of auditory, shallow processing. And words that were subject to either visual or auditory processing tasks were recalled far less well than the words that were given the meaning-based task. So essentially, Craik and Tolving's hypothesis that deep processing leads to better memory for the words was confirmed relative to shallow processing. So the idea of levels of processing has many implications and applications. First of all, it implies that simply using deep or meaning-based encoding strategies can improve memory without any additional investment of time and effort. This can be useful for students who must master large amounts of material in a relatively short periods of time. Many literature students have to read many books in a very short period of time, especially if you're in grade books, and then remember many details about them. Consider preparing for a quiz on a particular novel. Concentrating on the ideas in the novel, probably what your literature professor is after, will help you remember the details about the book that you also need to know for the quiz. It's a win-win. The ultimate goal is to understand the novel, the author's intentions, and how they play out in the plot and the characters. When you focus on the big picture, details follow. Deep levels of processing can also improve memory in areas in which you might not think it would help, namely memory for visual information. For example, the levels of processing framework predicts how well people can remember faces. Deeper levels of processing lead to better memory for faces, even though the test itself requires one to recognize visual images of faces. Sporer in 1991, for example, showed that people were better at recognizing faces if they had first processed them in terms of whether or not the face looked honest than if they had processed it in terms of whether or not the person had a wide nose. Judging for honesty is similar to the meaning-based processing we have been discussing, whereas judging the physical characteristics of the face is clearly shallow processing. Although most of us would agree we should not judge a person's honesty by how they look, doing so allowed participants to remember those faces better later on. In contrast, consider an experiment designed to determine if maintenance rehearsal benefits long-term memory. In this study, Craig and Watkins in 1973 gave participants a list of words to read. Most of the words were to be read silently, but if a word started with a pre-designated letter such as B, participants were supposed to repeat that word aloud as they read the rest of the list. Thus, if the word was boat, they would say aloud boat until they reached another word that started with a B, such as bagel. Craig and Watkins varied the number of words that occurred between one B word and the next. Thus, bagel might follow boat only by 3 words, whereas belly might not occur until 10 words after bagel. In this way, Crick and Watkins were able to vary the amount of time participants spent engaging in maintenance rehearsal. Thus, if maintenance rehearsal led to long-term retention, the longer the time spent in maintenance rehearsal, the better that memory will be. The outcome was that it didn't matter how long people engaged in maintenance rehearsal, recall was the same across the number of intervening items. Maintenance rehearsal allows people to keep information in working memory, but does not create good long-term memory, episodic or otherwise. So elaborative rehearsal, whereby you think about meaning, is much more effective than maintenance rehearsal when it comes to encoding information into long-term memory. However, there have been critiques of the levels of processing theory. So one major criticism is that the theory is circular. That is, anything that produces good memory performance is thought to involve deep processing. So in this view, deep processing is not defined separately from good memory performance. Aware of this possibility, Fisher and Craik in their 1977 paper showed that under some conditions, deep processing produced worse memory performance than did shallow processing. The key was the test. If the test involved shallow processing, then encoding via shallow processing was better than deep processing. If the test required the participant to recall perceptual details, such as the color of a written word, then processing for color led to better recall than processing for meaning. Thus, in this case, deep processing was defined independently of a positive effect on memory. The self-reference effect refers to the observation that linking to-be-learned information to oneself personally, or linking to-be-learned information to information personally relevant about oneself, creates strong encoding. To demonstrate the self-reference effect, Rogers, Culper, and Kirker in 1977 found that relating information to oneself was particularly useful in creating strongly encoding memory traces. In another study, Kelly and colleagues 2002 showed that words that referred to personality traits were more likely to be recalled if the person applied that trait to himself or herself than if she did not. Kelly and colleagues also found that when people applied these traits to themselves during encoding, there was increased activity in the prefrontal cortex, including the anterior cingulate, relative to when they did not apply traits to themselves, as measured by functional magnetic resonance imaging, or fMRI. The anterior cingulate is the area in the prefrontal lobe associated with, among other things, novelty, surprise, and cognitive conflict. Activating this area makes a stimulus particularly distinctive. Lesh, Leshkar and colleagues 2015 found that self-referencing was equally effective for older adults as it is for younger adults, suggesting that relating materials to oneself is a good way to offset natural age-related declines in memory. Finally, Sullivan and colleagues in 2018 showed that writing words and then pulling those notes toward oneself rather than away from oneself led to better memory for the words. Klein 2012 argued that although it is difficult to psychologically define a unitary self, there are several independent self-reference effects, all of which contribute to increased encoding power for those items that are processed relative to oneself. So just to review some of those experiments demonstrating the self-reference effect again, Rogers and colleagues in their seminal 1977 study, for their design, they had participants process a list of adjectives under different conditions. So in the structural processing condition, they were asked, is the word in uppercase letters, right? So that would be an example of visual shallow processing. And then in the phonemic processing condition, they were asked, does the word rhyme with X, which is an example of auditory shallow processing. In the semantic processing condition, they were asked, does the word mean the same thing as Y, right? So that's an example of deep processing because they're processing for meaning. And finally, there was a self-relevant processing condition. Does this adjective describe you? Okay, so the word might be intelligent, smart, sassy, bored, etc. And if the participant believed that that adjective described them, they would say yes or no if it didn't describe them. And ultimately what they found is that words processed in the self-relevant condition were better recalled than the words in any of the other conditions, including the deep processing condition. So the conclusion is that self-relevant processing or self-referent processing is superior to any other type of memory retention strategies, including deep processing. In 1997, Simmons and Johnson published the first meta-analysis on the self-reference effect, where they reviewed multiple studies, and they found that the self-reference effect is robust and consistently shows that encoding for self-relevance improves memory performance across a wide range of different tasks. And the implication is that the effect is generalizable across many different types of materials as well as diverse populations. And in this experiment by Klein and colleagues, participants were asked to evaluate adjectives, and they were asked two questions. So they basically had two processing tasks. For some of the adjectives, they were told, does this adjective describe you? And for other words, they were asked, does this adjective describe most people? And what they found is that adjectives that were judged in relation to the self were better recalled than the adjective judged in relation to other people. So the conclusion is that self-relevant information, or information that refers to the self, is going to be encoded more deeply and recalled more accurately than information that's relevant or referent to other people. And in this study by Kasaber and Oyashi in 2010, they examined the self-reference effect in different cultural contexts, and they found that both individualistic and collectivist cultures showed the self-reference effect, although it was slightly stronger in individualistic cultures like the United States and the United States and Europe relative to various Asian countries. So the conclusion is that the self-reference effect is a universal phenomenon, but it does vary slightly by cultural context. So there are multiple explanations for possible mechanisms that cause the self-reference effect. So the best supported explanation is the depth of processing explanation. And that's simply that information related to the self is processed more deeply than other types of information, leading to better memory retention. The elaboration hypothesis is that information that's referent to the self is often more elaborated, meaning individuals create richer and more detailed representations of information. Another possibility is distinctiveness. So information related to oneself is more distinctive and unique, making it easier to retrieve and less likely to be vulnerable to processes such as proactive and retroactive interference. And the last potential hypothesis is emotional involvement. Self-referent processing often involves greater emotional engagement, which enhances memory consolidation, as it includes processing not only by the frontal regions and the hippocampus, but also other areas within the limbic system, such as the amygdala, right? And the more distributed processing you have in the brain, or more dispersed patterns of activation you have in the brain, the richer your representation or memory trace is going to be. So imagine that you are lost in the desert without food or water or a compass to guide you back to civilization. You must survive on your own using the plants and animals you find along the way. You must also avoid predators such as lions and leopards, which may be hiding behind every boulder. What would be useful to you under such circumstances? A radio, opium, a priest? So Nairn, in their 2010 paper, argued that evaluating information in terms of its relevance to survival increases our ability to encode and retrieve that information. And indeed, this type of encoding may be particularly deep and self-relevant encoding, and that strategy may have served our ancestors long ago as well. So to test this idea, Nairn, Thompson, and Pandiria in 2007 asked asked participants to rate a group of unrelated words in terms of how relevant they were to surviving on the grasslands of a foreign land. Nairn and colleagues defined this type of processing as survival processing. They compared subsequent memory for these words with words that had been learned under a variety of other orienting tasks, including rating the word for pleasantness, usually considered a deep level of processing because it focuses on the meaning of the words. Interestingly, the survival scenario led to 10% better recall than did the pleasantness judgment or judgments about surviving in a city. Right? So this result has now been replicated numerous times, and Nairn 2010 argued that a memory system that operated in this way would have been selected over evolutionary time, and it may be that factors such as meaningful processing reflect these ancestral concerns. Either way, the next time you have to study for a test, right, it might be helpful to imagine you are studying on the African savanna surrounded by hungry lions, right? And you just may do better on that test than you would have, and it may be fun as well. So survival processing is processing information in terms of its value to surviving in the wilds is a surprisingly effective manner in which to encode information, right? According to the levels of processing framework, anything we do to increase elaborative or meaning-based processing will strengthen an item in long-term memory. The generation effect refers to the fact that memory is better when we generate associations ourselves than when we simply read them. So, for example, Slamecka and Graf in 1978 demonstrated this effect in a particularly clever way. They controlled the material so that generating items would be trivially easy as it was to simply read the materials. If memory performance was better for generated items, it would not be the result of the extra effort used to generate the items, but because the person generated the items himself or herself. Here is how they conducted the experiment. Participants in the experiment knew that their memory for the associations would be tested, so the task was intentional learning, unlike the incidental learning tasks utilized by Craik and Tulving. The participants also knew they would see a left-hand cue word of a paired associate and have to remember the right-hand target. Encoding the items was done in one of two ways. In the read condition, participants simply read the pair of items, but in the generate condition, they followed a rule that allowed them to generate the same target item as was provided in the read condition. The generate condition is rather easy. Almost all participants successfully generated the expected target word without error. As you can see, it takes little mental effort to generate the word crash. Yet, the effect on memory performance was profound. Recall of the target words was 28% better in the generate condition. The effect is not limited to paired associates in the laboratory. It also works in real-world settings. So, for example, Butler and Roediger in 2007 tested it in a simulated classroom setting. Participants viewed 3 lectures on different topics over 3 consecutive days. After each lecture, some participants received a lecture summary equivalent to the read condition, whereas other participants received short answer tests equivalent to the generate condition, with feedback given to the participants on half of their answers. On the short answer test, the participants retrieved or generated the same item that was provided to participants in the read summary condition. A final control group of participants did not get a summary or receive a short answer test. 1 month later, the participants returned to take a test on the materials covered in the lectures. The group that performed the best on the final test was the group that had been given the short answer test, or the group that had to generate the answers. Thus, in real world learning situations, generating items can lead to better memory performance, as well as in typical laboratory conditions. Although Butler and Roediger called their effect a testing effect rather than a generation effect, the reasoning is similar. Right? So memory is better when we generate associations ourselves rather than we simply read them. Right? So, for example, in the read condition, participants would read rose followed by hose, whereas in the generate condition, they would have to generate crash when given the rhyming word mash, right? And whether they did this task in the laboratory or in a simulated classroom condition, where they either received notes following a lecture or they took a short answer test following a lecture, generating the information yourself always resulted in better recall. So besides deep processing and self-relevant processing and survival processing, another strategy you can use to enhance encoding of information into long-term memory is organization. So organization means imposing meaningful structure on to-be-learned material. So applying organization to new learning causes the learner to focus on meaning of the material and thus increases the depth of processing. So thus organizing what we learn into categories and making meaning-based connections is also a very effective way to improve encoding. So now what I'm going to do is I'm going to show you several examples of experiments that have shown that organization is helpful for long-term retention of information. So, for example, in 1956, George Miller did a lot of research on chunking, right? And that's a classic example that highlights the importance of organizational structure in memory encoding. He found that people can remember more information if it is chunked into meaningful units, right? So we had participants memorize a series of numbers or letters, and some sequences were chunked into familiar patterns, such as phone numbers, or broken down, letters were broken down into abbreviations like FBI, CIA, CBS, things like that. And he found that when the information was broken down into meaningful chunks or abbreviations or phone numbers, participants were better able to remember the meaningfully organized units or chunks of information rather than the just random list of numbers or letters. So chunking facilitates memory encoding by reducing cognitive load and providing an organizational structure that breaks down that information into meaningful units. So another study that demonstrated the importance of organization in memory was conducted by Bauer and colleagues in 1969. And basically in this study, they had two presentation conditions. So basically they had two different groups of participants that received two different types of lists. So they either received a highly organized list with kind of a graphic organizer. So, for example, they might see a picture that has a hierarchy of plants, animals, and tools and elements, right? So those are the four categories: plants, animals, tools, and elements, right? And so under each tree, you would have a group of plants, flowers, bushes, shrubs, whatever. And then different animals, maybe carnivores, herbivores, etc. And then under elements, you might have, diamonds or whatever, different types of elements. And then the participant could see through this organizational tree, which of the words belong to each of the categories and subcategories, right? So there's a hierarchical structure for each of the items. And then in the other condition, participants were just given a random list of words. So all of the plants were mixed in with all of the animals, which were mixed in with all of the elements. And there was virtually no organizational structure. And basically, what they found is that the people in the organization list condition that saw this graphic organizer recalled significantly more information than did the participants that had gotten the random list. Okay, so organization was found to significantly facilitate both efficient encoding and retrieval of the information. And they conducted multiple experiments in this particular paper, essentially finding the same results. So, for example, the average recall for the hierarchical organization group was around 65%, while the random group averaged about 19%. So really, the people in the organized condition were recalling about 3 times as much information as the random list condition. And they also found that while participants in the random no organization condition very quickly forgot the information and did even worse under distraction. So if the participants were given a concurrent task, such as a digit span, so having to study these lists of words and also remember random strings of numbers, people in the random condition did very poorly on both tasks, but participants in the organizational condition were still able to remember quite a lot of the list. So the conclusion is that having a hierarchical organizational structure facilitates the encoding of information, and it also enhances retrieval, even in the face of distractions such as the concurrent task. Another really famous paper supporting the role of organization in facilitating both encoding and retrieval of information in memory was conducted by George Miller in 1967. So, in his paper Organization and Memory, he essentially conducted an experiment where participants were split into 2 groups. One group of participants received a list of words along with suggested categories for the words, while the other group received the same list without suggested category labels. And so the results were that the participants who were able to use categories to organize the list of words and split them into groups were better able to later recall the words than participants that were not given this categorical structure. So the conclusion was that having conceptual memory aids like categories facilitated encoding by allowing the participants to group the items together, which made retrieval easier. And obviously, the category label also provided a cue, which enhanced memory for the items as well. So we know organization is beneficial for memory encoding and retrieval in episodic memory, but what are some of the neural substrates? Or what happens in the brain under organized encoding as opposed to random unorganized encoding? So one study by McClelland and colleagues took participants and scanned them in an fMRI machine while they studied either list of words presented in categories or list of words presented randomly. And what they found is that there was greater activation observed in the hippocampus and the prefrontal cortex when participants encoded the structured lists. So the conclusion is that the findings suggest that these brain regions are more involved in processing and storing organized information, highlighting the basis for many of the benefits of organizational structure in memory. So basically, the areas of the brain like the prefrontal cortex and the hippocampus that are responsible for encoding of information are more active or enhanced when you're utilizing organizational strategies. Another way that organization is beneficial for memory encoding is through the use of schemas and scripts. So, in this particular study, participants or the researchers examined rather how people remember routine activities by asking participants to recall details from common scripts, such as dining at a restaurant. And there were two conditions. So there was one condition where the event was very typical and would follow the schema that most people have for dining in a restaurant or going to a doctor's office. And there was another condition known as the atypical condition, where something sort of odd or strange happened that wouldn't sort of be consistent with your existing schemas. And what they found is that participants were able to recall a lot more details more accurately when the events followed a typical script as compared to when the events were random or atypical. So the study demonstrated that pre-existing schemas and scripts prove that sort of a useful framework for understanding memory encoding is that we follow kind of pre-existing schemas and scripts to not only organize information but also to predict what might happen in the future, right? So having a schema as an organizational structure is helpful for both encoding of information and retrieval of information. So thus far, we have focused on organizational strategies that enhance encoding and retrieval in episodic memory. But it's also possible to focus on distinctiveness, right? So organization, by definition, is a strategy that focuses on the similarities or commonalities between the types of information that we're studying, right? So all of the animal words would belong to the animal category, and all of the plant words would belong to the plant category, and etc. Right, so that's searching for similarities or commonalities among a list of words. But searching for distinctiveness can also lead to that same kind of deep processing, right? Because you're still making a comparison, right? So whether you're looking for commonalities that unite a category of words or distinctions between categories, in both cases, you're looking at the meaning of the word, and so therefore that increases deep processing. So the study of distinctiveness on memory actually has kind of an interesting history. So Hedwig von Restorff published an important paper on the effects of distinctiveness in memory encoding in 1933. And von Restorff was German and continued her work on distinctiveness until the Nazis interfered with her lab and forced the university she worked for to fire her. However, because of her seminal research, the advantage in memory that distinctive items have over less distinctive items is known as the von Restorff effect. So to illustrate the von Restorff effect, consider the following list of words: jump, hop, fly, swim, crawl, putter, vomit, run, skip, skate, flip, right? It's likely that you will notice the commonalities in this list, right? All of the words are verbs for movement, except the obvious exception, the word vomit, right? So it is likely that the word vomit will stand out, right? Also, while all of the other words are neutral or even pleasant words, vomit is decidedly an unpleasant word. So in addition to the fact that all of the other words convey some sort of motion, uh, uh, vomit, and I guess vomit is a kind of motion, but it's very different from the other words, right? So, whereas the other words, like I said, are either neutral in the sense that they don't evoke emotions, or pleasant in the sense that they evoke positive emotion, vomit is obviously a negatively valenced word, right? So this example is a very powerful illustration of the von Restorff effect. So, von Restorff showed that the distinctive item was remembered better than a category consistent word placed in the same serial position. So if you put a word in the list that was also a form of movement, like run or something like that, people were much less likely to remember that word than the word vomit, right? So the von Restorff effect is again just the phenomenon that distinctive words are remembered better than similar words that all follow a particular category label. And it's also known as the isolation effect. So in the von Restorff effect, participants are given a list of words to commit to memory. The words on the list are homogeneous along one dimension except for one word, which differs from the rest in terms of category, right? So for example, participants might study the list of names such as 11 birds, but also see the name of a boat like a kayak, right? And the typical finding is that the isolated or distinctive word is recalled much better than the other items in the same list. Okay, so that illustrates how distinctiveness can sometimes help with memory encoding. And again, just like organization, where we process information for similarity, processing for distinctiveness also taps into the meaning of the word, which engages deep processing. Okay, so we focused a lot thus far on encoding or getting information into episodic memory. So now let's focus on retrieval from episodic memory. So retrieval is the process by which information is recovered from memory. In episodic memory, we retrieve events, that is, specific individual happenings from our lives. So an event can include memories of what people said or did, or it can include visual images, and it can also include our emotions about the event. So availability refers to all the information present in our memory system. That is, everything you have ever learned and currently stored in your episodic memory. Availability can never be directly measured because although all of this information may be stored in memory, we can never retrieve it all at any particular time. In contrast, accessibility refers to the part of our stored memories that we can retrieve under the present conditions. At any given time, we may be able to access only some of our memories, but not all of them. Thus, availability and accessibility are very different concepts. As it turns out, the key to ensuring a memory is accessible is having the right retrieval queue, right? So retrieval queues refers to information in our current environment that helps us to trigger a specific memory for an event. So related to all of that is the encoding specificity principle. And essentially that stipulates that retrieval of information from memory will be maximized when conditions at retrieval match the conditions at encoding. That is, recall or recognition of information will be easier, faster, and greater in amount when there is overlap between conditions of retrieval and encoding. So the term condition can mean the physical location of the person, her mental state, emotional state, or even physiological state across both learning and retrieval. So research on the encoding specificity principle takes the following form. Participants encode information under one of two conditions. Then, after a retention interval or the passage of time, the participants return to either the same condition or the opposite condition in an attempt to retrieve information that they encoded. The typical pattern is that people recall better when they encode and retrieve under the same conditions. Our first example of this form of an experiment is a now classic study done by two British researchers, Godden and Badley, in 1975, who studied British naval divers. The participants were all trained scuba divers who were quite comfortable working underwater in scuba gear. Godden and Badley asked half of the divers to learn a list of words on a waterproof whiteboard anchored 15 feet underwater. The other half of the participants studied the same list of words on land. This is called the encoding manipulation. That is, the researchers established two environmental contexts at the time of encoding, land and water, and each encoding group was divided into two groups, a group that retrieved the words on land and a group that retrieved the words underwater by writing the list of words on the underwater whiteboard. This was the retrieval manipulation with two conditions, retrieving underwater and retrieving on land. Therefore, there were four conditions in total: encoding on land and retrieving on land, or encoding on land, retrieving underwater, encoding underwater, retrieving underwater, and encoding underwater and retrieving on land. And as you can see from the results in the graph, those that encoded the list on land and were also tested during retrieval on land, and those that encoded the list underwater and were also tested underwater showed significantly better recall than those that were either encoded the information underwater and were tested on land, or encoded the information on land and were tested underwater. Right? So basically, the idea with the encoding specificity principle is that when the physical environment you were in during encoding matches the physical environment you were in during retrieval, okay, you'll show better recall for that information than when the physical environments during encoding and retrieval are reversed, right? So if you were tested underwater, or if you learned the information underwater and were tested underwater, you did better than if you learned the information underwater and were tested on land. If you learned the information on land and were tested on land, you recalled more of the information than if you learned the information on land and were tested underwater, right? So matching the physical conditions between learning and test leads to better recall than when the conditions between learning and test are mismatched. When encoding specificity is implied to internal human states, such as a drug state or a mood state, it is also referred to as state-dependent memory. In one of the more daring demonstrations of state-dependent learning and the encoding specificity principle, Ike and colleagues, 1975, examined the influence of marijuana on people's memory. In an ad in the University of British Columbia newspaper, they recruited smokers to participate in this study. On day one, the participants were either given a marijuana cigarette or a tobacco cigarette. The researchers then waited about an hour for the drugs, THC and nicotine respectively, from each of the cigarettes to enter the participants' bloodstream. Then the participants were given a list of unrelated words to study. The participants were dismissed and asked to refrain from smoking for the ensuing 48 hours. This was important to ensure that the drugs would be eliminated from the participants' bloodstream when they returned for the recall test. When the participants returned, they were again given a cigarette to smoke. One of the participants who had originally smoked marijuana Of the participants who originally smoked marijuana, half again smoked marijuana and half smoked tobacco. Likewise, of the participants who had originally smoked a tobacco cigarette, half again smoked tobacco and half smoked marijuana. The results were strikingly similar to those of Godden and Badley. The conditions in which encoding and retrieval were matched led to best recall. In this case, the two conditions that led to best recall were when participants had smoked the same drug at both encoding and retrieval, the marijuana and marijuana condition, and the tobacco condition. The mismatched conditions in which the people smoked different drugs at different times led to relatively poor recall. In a follow-up study, Ike 2008 found similar results for alcohol. Thus, encoding specificity holds for drug-induced cognitive emotional conditions as well. So whether we're talking about being in a state of alcohol intoxication, marijuana intoxication, or tobacco intoxication, your memory is going to be better if the conditions at encoding match the conditions at retrieval. So Ike and Metcalf in 1989 conducted another experiment that examined whether mood states were subject to the encoding specificity principle. Like the earlier studies, they had two encoding conditions crossed with two retrieval conditions. In their study, they tested Canadian college students by inducing them into either happy or sad moods by having them think either happy thoughts while listening to happy music or thinking sad thoughts while listening to sad music. And this was sufficient to induce most of the students into either a happy or sad mood. Right? So some of the students were sad when they encoded a list of words and were also sad when they were tested on that list of words. Whereas other students were happy when they studied the list of words and also happy when they were tested on the list of words. And two other groups were mismatched. So they were happy when they encoded the words and sad when they were tested, or sad when they studied the words and happy when they were tested. And what they found is that participants recalled significantly more words when they were sad for both study and test or happy for both study and test compared to when they were the emotions were mismatched. So they refer to this as mood-dependent memory, but it's basically just another example of the encoding specificity principle, just applied to mood in this case. So a lot of times mood-dependent memory is confused with another effect known as mood congruent memory. So mood congruent memory simply refers to the fact that when you are in a happy mood, you tend to focus more on happy memories, right? So if you just get proposed to by your significant other, that fills you with positive feelings, and you probably are filled with all kinds of happy memories of dating your significant other and all of the fun that you had, doing various activities together. Whereas if you get in an argument with your significant other and that puts you in a bad mood, you're much more likely to focus on previous arguments or things about that person that make you sad or angry, right? So mood congruence just means that we tend to retrieve memories that are related to our current mood, right? Whereas mood dependence is a form of encoding specificity where your mood acts as a retrieval cue, right? And so if you're in the same mood during study and test, you're going to recall more information because of the fact that you're in a similar internal state, right? So what mood-dependent memory and state-dependent memory and encoding specificity, all of these experiments, what they illustrate about memory is strongly cue dependent, right? So in the case of the Godden and Badley studies, the physical environment, whether you're underwater or on land, acts as a very strong retrieval cue. In the Ike and Metcalf studies looking at internal state, whether it's drugs or your mood, those substances or experiences also act as retrieval cues that help you to access that information at test, right? So one last memory phenomena that I wanted to talk about was something called transfer appropriate processing, or TAP. And that's a cognitive theory that suggests that memory performance is not solely dependent on depth of processing, but rather on the congruence or similarity between the processes involved during encoding and retrieval. So in essence, transfer appropriate processing posits that memory retrieval is most effective when the cognitive processes engaged during encoding match the processes engaged during retrieval, right? So transfer appropriate processing challenges the traditional depth of processing theory, which posits that deeper semantic processing of information leads to better memory performance. Transfer appropriate processing, on the other hand, emphasizes the importance of the type of processing. If the retrieval conditions match the encoding conditions, memory performance improves regardless of the depth of processing. And so transfer appropriate processing actually provides an explanation of the of the Craik-Ferguson study that I talked about earlier, where they found that if the test involves visual processing, like figuring out what color something is, that shallow processing was actually better than deep processing, right? So that suggests, again, what matters is the congruence of the type of processing between both encoding and retrieval rather than the depth of processing. So what evidence do we have in support of transfer appropriate processing? Well, Morris and colleagues gave participants words and asked them to perform either a semantic processing task, which was judging whether a particular word fits in a sentence. So for example, seeing the sentence, the blank crossed the road, and the word was boy, right? So that sentence makes sense. The boy crossed the road. So the participant would say yes. Or if the word was I don't know, box, the box crossed the road, the participant would say no, that doesn't make sense, right? So that's semantic processing. And they also had a rhyming task where they were given a word such as train as the target word, and they were asked, does this word rhyme with boat? And the participant would say, no, train doesn't rhyme with boat. So later participants were tested on their memory for the words using either a semantic recognition test or a rhyming recognition test. And basically the results is that performance was better when the encoding task matched the retrieval task. So specifically, when participants engaged in rhyme judgment, they remembered words better on the rhyme recognition test, as opposed to those who engaged in the semantic judgment task performed better on the semantic test. So the conclusion is that this experiment demonstrates that memory is most effective when the processes engaged during encoding and retrieval are the same, supporting the transfer appropriate processing hypothesis. Next, we have an experiment by Roediger and Blackston in 1987. So essentially, they extended the transfer appropriate processing concept to include the effects of context and the nature of the retrieval task. So what they did is they had participants study word lists with different types of encoding tasks. So for example, they might have a list of words and have to give either a semantic judgment, which is similar to the experiment I just showed you, or a phonological judgment. So a semantic judgment might be something like, does this word make sense in this sentence? Whereas a phonological judgment might be, does this word have 2 syllables? Or does this word rhyme with this other target word? And they found that memory performance was better when encoding and retrieval tasks matched. Okay. And lastly, this study by Wheeler and colleagues in 93, participants were asked to engage in tasks that either required semantic processing or surface level processing. So they might be asked, does this word make sense in this sentence, or does this word have capital letters? And later they performed tasks that either matched or mismatched the initial encoding tasks. And the results were that participants performed better on memory tasks when the encoding and retrieval processes were matched. So for example, those who had processed the information semantically had better recall on the semantic tasks, whereas those individuals that had studied the information visually had better recognition on the visual tasks. Right? So there we see that not only the levels of processing, but also the congruency between the type of processing across encoding and retrieval influences what is remembered. Thank you so much for your attention, and I hope you have a wonderful day.